Hello everyone, I'm Zane from UC Davis, and today I will tell you about our paper, Doing Good by Fighting Fraud, our work on ethical anti-fraud systems for mobile payments. Smartphones and apps are everywhere and can be used for anything from food deliveries to money transfer to bookings to banking and much more. However, this ubiquity has also led to new classes of attacks like payment fraud, identity theft, money laundering, etc. Concretely, let's take an example of payment fraud. Attackers carry out payment fraud by acquiring stolen payment card information online, and then this information is used to make purchases with these apps without possessing the physical card. For instance, the attackers could pay for drug runs on ride-sharing apps with these stolen cards. Or they could act as agent service, offering goods to legitimate users at a discount while paying the app with stolen cards. In the example on the slide, the user pays $5 to the attacker for a burger. The attacker places an order with the app on behalf of the user, paying the full $10 with the stolen cards while pocketing the $5 from the user. The app treats this as normal transaction, delivers the burger to the user, who effectively gets it at a discounted price. Meanwhile, when the real owner of the stolen card sees this transaction on their bank statement, they dispute the transaction. Upon investigation, if the bank finds this transaction is fraudulent, they'll issue a chargeback to the app. The app will have to pay back the money to the real owner of the card and an additional dispute fee to the credit card company. So not only does the app lose money, but it's also being used for illegal activities like drug runs, as mentioned before. This process can also be abused to move money around. Naturally, it's no surprise that apps take fraud seriously and commission data scientists to build fraud prediction models. Fraud engineers can use features from the transaction or the user together with the chargeback data to train fraud prediction models. The chargeback labels from the bank serve as the ground truth for the transactions. However, chargeback data takes a lot of time, in some cases up to 90 days to accumulate. Also, users may not flag a transaction as fraudulent, in which case the transaction is mislabeled. Additionally, in the training data, if there's bias towards a certain attribute or an attribute correlated with a protected attribute, this can lead to discrimination. Now, companies need to block fraud to keep costs down, or else low-income populations can't afford the service. But algorithmic bias in the anti-fraud models might block them anyway. For instance, if there is bias in the historical data pertaining to zip code, the fraud decision engine could amplify that bias by predicting more fraud for that attribute. And this data then gets fed into the training pipeline, again, creating a positive feedback loop. This is just one example, and there are multiple ways in which bias can creep into the decision engines. So this is an ethical catch-22. Like, what do we do? To reduce the impact of mistakes by fraud algorithms, apps have developed user-facing challenges, where the app requires suspicious users to pass a challenge instead of suspending the user or blocking the transaction. So even if the algorithm has bias, these challenges provide an avenue for making sure that everyone can access the app. Like Uber's card scan, where a suspicious user is asked to scan their card to prove possession, or Jumio's ID and liveness check. So then the question is this it? Are user-centric challenges the silver bullet? To answer this question, we performed a measurement study of Boxer, an open-source anti-fraud SDK. Based on our measurements, we found that Boxer doesn't perform well on resource-constrained devices as opposed to well-provisioned ones. For instance, there is a 105x performance difference between iPhone 11 Pro Max and Samsung J320. And this has the potential of reinforcing existing bias against at-risk populations. These user-facing challenges need to work for all users, otherwise they are self-defeating. Later on in the presentation, I'll introduce our system that empowers these challenges to run on a wide range of devices. In the remainder of the presentation, I'll first talk about our measurement study of Boxer and the implications from the results. I'll then introduce our new system, Daredevil, that provides an equitable framework for user-centric challenges. This will be followed by the evaluation of Daredevil in a production environment, and afterwards I will conclude. In this paper, we conducted the first large-scale measurement study of a security challenge using deep learning on mobile devices. Our measurements focus on Boxer, a widely deployed state-of-the-art open-source card scanner, which is used as part of an anti-fraud SDK. So the way it works is, given a payment card image, the card scanner uses deep learning models to extract the card information from the image. The first question we wanted to answer with our study was, what is the raw performance of the system? What percentage of users can use the system successfully? And then, is the performance correlated with any measurable factors? In other words, if we want to improve the system, where can we begin? With these goals in mind, we instrumented the Boxer SDK and shipped it in 496 apps. We report the anonymous statistics sent by these apps from July 2019 to November 2020. Our instrumented Android SDK ran on over 300,000 Android devices spanning 611 device types, whereas our iOS SDK ran on over 3 million iOS devices spanning 27 device types. We measured two key performance metrics. The first one was success rate, which we defined as the ratio of the number of devices where the card scanner was able to extract the card information correctly to the total number of devices. And frame rate, which we define as the number of frames from the camera processed by the deep learning models of the card scanner per second. Here are the results. The figure shows the variation in success rate plotted against frame rate for iOS. The x-axis is the frame rate, whereas the y-axis is the success rate. Each point represents the average for a specific device type. It is clear that improving the frame rates increases the success rates. So investing in efficient machine learning inference impacts the end-to-end results from an end user as well as from a business perspective. However, when we plot the results for Android, unfortunately, it doesn't paint a rosy picture. We see that both success and frame rates are significantly lower despite using the same machine learning models and algorithms as iOS. In fact, there is a precipitous drop in success rates as frame rates drop below 1 to 2 FPS. Here are the aggregate results for iOS and Android. For context, higher success rates means better system. And you can see that while the success rates for iOS is 88.60%, the success rate for Android is much lower at 46.72. To further analyze the results on Android, we group the success rates by frame rate. We can see that a significant portion of the devices operate at frame rates less than 1 FPS and exhibit very low success rates. One interesting point to note in all of this is that if we aggregate iOS and Android results, we see that Boxer works well on 93% of the devices. In other words, Boxer is a successful system overall and solves the app's business problem, since Boxer will recover most of the people that the app flags incorrectly, which is its primary purpose, right, to unblock users. However, by blocking devices that are unable to run Boxer models fast enough, it runs the risk of denying at-risk populations. To understand why frame rates and success rates are related, here's a simple thought experiment. Say we have a fast phone and a slow phone. The ML models on the fast phone can process 10 frames per second, whereas the ML models on the slow phone can only process 0.5 frames per second. So if a user scans for 10 seconds and then gives up, the fast phone processes 100 frames, while the slow phone processes only 5 frames. In other words, the machine learning models on the fast phone will see 20 times more data than the ones in the slow phone for the same amount of time. In case of a security challenge, this can lead to blocking of an end user simply because they have an inexpensive device. Now, if the security challenge never runs due to limited resources on the end device, the decision engine will not have the data needed to unblock the user. And we cannot merely rely on algorithmic notion of fairness since it cannot account for the lack of this data. We need the end data from the end user. And to this end, we present Daredevil, which is our system for running card scanning and verification on full range of devices one is likely to see in practice today. We believe that Daredevil is a more equitable framework for fighting fraud. Due to the time constraint, I will not be able to go into the inner workings of our system, and I encourage you to read our paper for more details. However, I do want to briefly talk about some high-level principles that were useful in designing the system. There are basically two key areas where we focused most of our time. The first one was the design of the machine learning models, given the kind of hardware these models would run on. And the other one was how and when to run these models to maximize efficiency and accuracy. In other words, the design of the optimal system pipeline. In designing our machine learning models, our first guiding design principle was to optimize for resource-constrained devices. Machine learning optimizations for resource-constrained devices translates to well-provisioned devices as well, but the reverse is not true. In other words, if a system is efficient for a CPU, it will also perform reasonably well on custom hardware, but the reverse may or may not be true. Our second principle was to optimize for the most common card designs. We observed that to support complex card designs, we needed to add complex auxiliary layers to our models, significantly increasing the inference time. And every card design will have to pay this extra inference cost. So we decided to natively support only the most common card designs and employ a gated pipeline for more complex card designs, keeping the inference efficient for the common case. From the system design point of view, our principles revolve around decomposition of the tasks. This has two benefits. The first one is efficiency. Say you have a task that requires running a complex machine learning model, you also need to know when to run this task, because if you run this task all the time, it'll just waste computation. In other words, this task needs to be broken into two subtasks. The first task is whether to run the task, and the second one is running the actual task. So both can be accomplished by machine learning models, one simple, one complex, where the complex model gates the execution, where the simple model gates the execution of the complex model, keeping the pipeline efficient. Decomposition also creates opportunities for redundancy, providing more avenues for error correction and overall improved accuracy. For instance, if you have one model that extracts the digits from the payment card and the other model that identifies design elements, these two models can reinforce each other, where the first model can be sure that the digits belong to an actual card and not some random string. To evaluate Daredevil, we conducted a similar experiment as our measurement study. We shipped the card scanner part of the Daredevil SDK in 114 apps, and we report the anonymous statistics sent by these apps from December 2019 to November 2020. Our Android SDK ran on close to 500,000 Android devices spanning 722 device types. The detailed breakdown is mentioned in the paper. And our iOS SDK ran on 1 million iOS devices, ran on over 1 million iOS devices, spanning 28 device types ranging from iPhone 5s to iPhone 11 Pro Max. As before, we defined success rate as the ratio of the number of devices where the card scanner was able to extract the card information correctly to the total number of devices, and frame rate as the number of frames from the camera processed by the deep learning models of the card scanner per second. The figure shows variation in success rate plotted against frame rate. The x-axis represents the frame rate and the y-axis represents the success rate. Each point represents the average for a specific device type. We plot these results for Daredevil deployed on Android and iOS against Boxer on iOS. As we can see, Daredevil's improvements increase the success rates on Android to closely match the success rates on Boxer iOS. Here are the aggregate results for iOS and Android for both Boxer and Daredevil. Compared to Boxer, we see that Daredevil on Android improves the average frame rates from 1.3 to 4.1. We also see that Daredevil Android increases the average success rates from 46.72% to 88.46%, closely matching the success rates on Boxer iOS. To further analyze the results on Daredevil Android, we group the success rates by frame rate. And compared to Boxer, Daredevil's architecture reduces the number of devices that operate at frame rates below 1 FPS from 44.61% to 4.88%. Like Boxer, with Daredevil, we see that the success rates for Android devices with frame rates less than 1 is lower than average. However, the overall increase in the number of devices that can run Daredevil at greater than 1 to 2 FPS leads to higher overall success rates. In addition to extracting card information, we also evaluated Daredevil's ability to stop fraud in real time, and we report the results from a large international app deploying our SDK. For a period of 3 months, the app flagged 12,474 transactions as suspicious and challenged them with Daredevil to verify their payment method. Daredevil passed 7,612 transactions and blocked the remaining 4,862 transactions. Of the 6,612 transactions passed by Daredevil, only 12 resulted in chargebacks, leading to a false negative rate of 0.16%. The app didn't share the false positive data with us, so we're unable to report the false positive rate. However, we ran an in-lab experiment evaluating Daredevil's false positive rate. Please refer to our paper for more details on the experiment. To answer the question of whether our fraud decisions are correlated with frame rate being our proxy for resource-constrained devices, we analyzed the performance characteristics of the passed and blocked devices. The average frame rate of devices that Daredevil passed was 1.84 FPS, and the average frame rate of the devices that Daredevil blocked was 1.94 FPS, indicating that the frame rates for the two groups is roughly the same. To visualize the results better, here's the CDF of the percentage of devices versus frame rate for the passed and blocked groups. The plots look very similar, indicating that the frame rate is not a discriminating factor between blocked and passed groups, further demonstrating the equitable nature of Daredevil. To conclude, we investigated the implications of deep learning-based security challenges in the context of apps. With data from over 5 million devices, we first demonstrated the disproportionate performance impact where user-centric challenges can solve the app's business problem, but also have the potential to disproportionately block users from lower socioeconomic tiers. We then designed, deployed, and demonstrated the equitable nature of our system Daredevil by empowering these challenges to function uniformly on a wide range of devices. That's it from us. If you have any questions, please email your questions to the email addresses mentioned on the slide. Thank you for your attention.